In the study of vector calculus in Math 22, we have seen how useful the dot product is in understanding and describing the vectors and surfaces in R3. In the last video, we extended the concepts of length and distance to higher dimensional vector spaces Rn. So in this video, we're going to extend further the concepts of length and distance to general vector spaces. This can be achieved by using the notion of inner product of two general vectors. So let us recall from the last video that the dot product on Rn satisfies these four properties. So these four properties will be the defining conditions for an inner product. So given a vector space V, an inner product on V will be a function from V cross V to the set of real numbers. So it's a function whose input is a pair of vectors and whose output is a scalar. Okay, so this function will usually be denoted by this symbol, left angle, dot, comma, dot, right angle. And this function must satisfy the following properties for any three vectors x, y, z, and any scalar c. So first, the inner product of x with itself should be non-negative. Okay, so actually, the inner product should be a function from v cross v to the set of all non-negative real numbers. And the value of the inner product is 0. Rather, the value of the inner product of x with itself is 0 if and only if x is the 0 vector. Next, the order of the first and second components should not matter when we compute for the inner product. Okay, so the inner product of x and y should be the same as the inner product of y and x. And it should satisfy this distributive type of property. The inner product of x plus y with z should be equal to the inner product of x with z plus the inner product of y with z. Okay. And finally, you should have this property for scalar multiples. So the inner product of the scalar multiple of x by c with vector y should be equal to the product of scalar c with the inner product of x and y. Okay, so beware of what's happening in both sides. So in the left hand side, we are taking the scalar multiple. So this guy here is a vector, but here we are multiplying c by the inner product. So this is usual multiplication of numbers, real numbers. Okay, so these are the four defining properties of an inner product on a vector space. And a vector space endowed with an inner product as above will be called an inner product space. Some remarks about this definition. Note that the definition of inner product may vary from text to text, so caution must be exercised. Also, properties B, C, D in the definition imply that for all vectors x, y, z and all scalars R and S, we have these values or these formulas. Okay, So property C implies that this inner product equals the inner product of Rx with Z plus the inner product of Sy with Z. But then if you apply property D to the result, you will obtain this expression. Take the inner product of X with the linear combination of Y and Z, then you can interchange the two. Okay? And then by the result here, this inner product will be equal to the inner product of Ry and X plus the inner product of Sz and X. And then applying property D and property B, that result will be reduced to this expression. So an immediate example is Rn with the usual dot product. Okay, so the dot product on Rn is an inner product because as we saw in the first slide, the four conditions in the definition of an inner product are satisfied. And this dot product on Rn is what we call the standard inner product on Rn. So by definition, Rn together with this inner product, together with the standard inner product, is an inner product space. So here we give a non-example of an inner product. So in R3, okay, let's define the function given by x comma y equals x1 y1 minus 2x2 y2 plus x3 y3. If x has components x1, x2, x3, and y has components y2, y1, y2, y3. So this is not an inner product because you can check that if we take x equals 1 to 1, the vector 1 to 1, then the first condition fails. Okay? The inner product of x with itself equals 1 times 1 minus 2 times 2 times 2 plus 1 times 1. Okay? So that's 1 minus 8 plus 1, so negative 6. It is negative. In condition A, we require that for any vector x, the value of x comma x is non-negative, greater than equal to 0. So this is not an inner product. Rather, this guy is not an inner product on R3.